right, we left off at Chapter 5, gas laws. All right, so PV is equal to nRT. Excellent chance that there will be at least one of those questions on the exam. So an example would be calculate the volume of 5 grams of nitrogen gas at 22.2 degrees Celsius and 745 millimeters of mercury. You're going to be given two R values. You're going to have the 8.314 and you're going to have the 0.08206. All right, and the units tell you which one that you need. This one is joules per mole Kelvin. That is not the one you need. You need liter atmosphere per mole Kelvin. So you have to use that one, which also means that your pressure has to be in atmospheres. Your temperature has to be in Kelvin, and N is moles. All right, so this one, so you have to do all your conversions. So let's do the pressure. Pressure is given as 745 millimeters of mercury. And you have to know that you're going to have to divide that by 760 millimeters of mercury in 1 atmosphere. So you have to know that conversion. All right, volume, that's what we're looking for. So volume, that is the question. We're going to have that answer in liters. All right, N is moles. All right, and but we have grams. 5.00 grams, and this is where it gets difficult because it's nitrogen gas. So within this question, you have to know the 7 diatomic elements. You've got your nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Makes a nice 7 on the periodic table, but don't forget hydrogen because that's only 6. So when it says nitrogen gas, you have to know that that means you have N2. So this is grams of N2, nitrogen gas. And so that has a molar mass of 28.02 grams per mole of N2. All right, so we will have then our pressure in atmospheres. We have our N in moles. The R is the 0.08206, and then our temperature, we got to take our 22.2 degrees Celsius, and we have to add 273.15 to get our Kelvin temperature, which is 295.4. All right, and so we did our sig figs there, because if you do it wrong, there's 3 sig figs, there's 5 sig figs, there's 4 sig figs. That's not doing it right. You are adding. There's 1 decimal, there's 2 decimals. So you give your answer to 1 decimal. That is the way you do sig figs for adding and subtracting. All right, and so we will get our answer because we're going to take our nRT and divide by our P to get the answer. Right. So 745 divided by 760. 0.980. That is our atmospheres. And then R we have, T we have, okay, that's P. So now we need N, 5 divided by 28.02. .178. All right, so then we plug in those numbers. We have our N value, 0.178. moles. We got our 0.08206 liter atmosphere per mole Kelvin. We have our temperature. It is 295.4 Kelvin. And then we have our pressure, 0.980. And so when we push all those buttons, we get our answer. All right, so we have our 0.178 right there. So times 0.08206 times 295.4 divided by 0.980, and we get 4.41 liters. All right, so there will be a question, and that's as hard as that question can get. You have to know your diatomic elements in order to get that one correct. You're also going to have to know Boyle's law, P1 V1 is equal to P2 V2. All right, and you also have to know that these just have to have the same units. Doesn't matter what they are. Same with this, same units. Doesn't matter what they are, they just have to be the same, and that's Boyle's law. If you have Charles's law, all right, so here, again, volume, same, has to be the same units. Doesn't matter what they are. Temperature must be in Kelvin. All right, most common error is you know how to do it, but you put your temperatures in Celsius, and that will give you the wrong answer every time. Make sure your temperatures are in Kelvin. Same with Gay-Lussac's law, P1 over T1 is equal to P2 over T2. Pressure doesn't matter, they just have to have the same units. But temperature must be Kelvin. All right, and then the combined gas law, which will answer all of those types of questions, is your P1 V1 over T1 is equal to P2 V2 over T2. All right, so again, same as right up above. Your pressure units, your volume units, they have to be the same. Temperature units must be Kelvin. Anytime you have just a T, it always has to be in Kelvin. All right, let's see. Partial pressures, a lot of times with partial pressures, you're going to have to know that your pressure total is equal to pressure of gas 1 plus pressure of gas 2 plus pressure of gas 3. You just add up all of the pressures of all of the gases. All right, so those are called partial pressures, and then you add up all your partial pressures, you get the total pressure. When you have a gas, many gases in the same flask, in the same room, all right, so it's in the same flask, in the same room. What that means is it has to have all gases in this vessel have the same temperature, and they have the same volume. And so if you do PV is equal to nRT, you see that the only thing that's not the same, because R is a constant, is your pressure and your moles. And so if you put your P over your N, so divide both sides by N, divide both sides by V, and you have RT over V. All right, so the temperature is the same, the volume is the same, temperature is the same, volume is the same, and R is a constant. So that's equal to a constant. All right, and so you could have that for any gas or even the total gas. So pressure total, moles total is equal to RT over V. And so you end up with your pressure of gas 1, moles of gas 1 is equal to your pressure total moles total. And this is important because a lot of times the questions are calculate the mole fraction. And all they give you is pressure units. That's it. And then you just solve for your pressure. So if you solve that equation, you get P1 over pressure total. And then that is one ugly 1. It's a 1. And that's equal to N1 over N total. And your moles over moles total, that is your mole fraction. So for gases that are in the same flask, they have the same temperature, same volume, the pressure fraction is exactly the same as the mole fraction. They may only give you pressure units for the problem. You have to know that for gases in the same flask, the pressure fraction is the same as the mole fraction. The other one is going to be if there is a gas collected over water. All right, when you collect a gas over water, that means your pressure total is going to be the pressure of whatever gas you're collecting. The one that I did in the lab was we collected the oxygen gas over water. All right, so that is the pressure total is the pressure of the gas plus the pressure of the water, and this you would get off of a table. So they're going to say the temperature was 20 degrees. You look at the pressure of water at 20 degrees, and this is going to be written on the board. This is the pressure of the day. It's the pressure in the lab. And so the pressure of your gas, you got to take your pressure of the lab, subtract your pressure of water to get the pressure of the gas. So if there is a problem that says you collected some gas over water, you have to know that you need to use this equation to find the pressure of that gas. Okay, chapter 6. Chapter 6, we did delta H. So whenever you're going to find your delta H of a reaction, you're going to take your delta H naught formation of your products. Going to add all those up and then subtract the delta H naught formation of your reactants. So you're going to have a chart of delta H naught formations. To get the delta H of the reaction, you got to add up all the delta H formations of your product, subtract all the delta H formations of your reactants, and you will have your delta H of that reaction. Remember, if delta H is negative, it is exothermic. If it's positive, it is endothermic. All right, Hess's law. This is when you add reactions. So when you add reactions, you add the delta H's. All right, so that's just adding up reactions. Now, if you have a reaction, so this could be a question, which should be a relatively easy question. Oh, let's say we are going to take methane and we're going to burn it. And we're going to get carbon dioxide and water. So this is a combustion. So to balance it, one carbon, 4 hydrogens. So we need 2 waters. And we've got 2 oxygens here. We got 2, 4. So we need 4 on that side. So here is the balanced chemical reaction. It's a combustion. We know that delta H is negative. All right, I'm just going to pick a random number. I'm going to say delta H is negative 200 kilojoules for this reaction. All right, so what's going to happen is then I'm going to say, all right, calculate the delta H for 2 CO2s plus 4 H2Os, yielding 2 CH4s and 4 O2s. All right, so this is a very likely question on the test. Is you're going to be given a reaction, and it's going to be given to you with some delta H value. Then they're going to change that same reaction, and you have to know what to do when they make those changes. All right, so the first thing you might notice is you reversed it. So the CO2 is now on the reactant side, not the product side. Remember, when you reverse a reaction, you have to change the sign of your delta H. All right, and so, but that's not the only thing that happened. We also multiplied through by 2. When you multiply through by 2, you have to multiply your delta H by 2. And so your delta H for this reaction is a positive 400 kilojoules. All right, again, we reversed it. That made it a positive 200. We multiplied it by 2. We had to multiply the positive 200 by 2. So make sure when you're doing Hess's law, you're going to have to do a lot of that. You're going to have to reverse things. You have to change the sign. You're going to have to multiply it through by some number. Make sure you multiply the delta H by that same number. So that is Hess's law. Chapter 7, electromagnetic spectrum, quantum numbers, and shapes. Okay. All right, so it could just be your it'll say which one has the highest energy. All right, and so you have to know your electromagnetic spectrum. And so it's going to go radio, micro, infrared, visible, ultraviolet, X-ray, and then gamma ray. All right, so your highest energy is the gamma ray, but it may say which one has the longest wavelength. All right, so you have to know a long wavelength is a weak energy. It's the weakest energy. All right, so highest energy is the gamma ray, and the longest wavelength is the radio wave. It could say what color has the highest frequency. All right, so you have to know that the higher the frequency, the higher the energy. And you also have to know Roy G. Biv for your visible light. All right, so the color with the highest frequency, which also means the highest energy, is violet. All right, so you have to know your electromagnetic spectrum. You have to know which one's a higher energy, which one's a higher frequency, which one's a longer wavelength. You need to know that for your electromagnetic spectrum, including your colors in the visible range. Let's see, we got quantum numbers, so we could do a 4, 2, 0, 1/2, and this is where it's going to be required to have a periodic table. All right, so what you can get without a periodic table from 4, 2, 0, 1/2 is you need to know that it is a 4, first number, you just write it down. Now the second number is L, which is going to be 0, 1, 2, 3, 4, 5, 6, and it's going to go to n minus 1. And this is S, P, D, F, G, H, I in alphabetical order. All right, and so when your L is 2, that means you have the 4D. All right, and what you need to know about D subshells is they have 5 orbitals. The one in the middle is always number 0. Then you have your -1, -2. You have your +1 and your +2. All right, and so we put in electrons. You have to know Hund's rule, which means we are not going to pair an electron here. We're going to put one electron in each one of those, and once there's one electron in, then we will pair it up. That's Hund's rule. All right, but we're not going to get that far because where we're going to stop is when we are at 0 with a spin up. All right, and so we stop at 0 with a spin up, and that means we put in 3 electrons. All right, and so now we need the periodic table to see what element the last electron put in is the 4d3. All right, and so when we have our periodic table, the first row of D is the 3d, the next one down is the 4d, and if you look at your periodic table on the 4d 3 over, that is NB is your element. So you have to know how to do your quantum numbers and the shapes of your orbitals. All right, so S orbitals are spherical. P orbitals are peanut shaped. And D are four-leaf clover shaped. All right, so you have your S is spherical, P is a peanut shape, and D is a four-leaf clover shape. Right. Electron configurations. All right, let's do. All right, if we want to do the electron configuration for bismuth, number 83. So you find number 83 on the periodic table. All right, the first prior noble gas is Xe. I always use the noble gas core. And then 55 is cesium, and that will start the 1, 2, 3, 4, 5, 6 S2. And if you follow your periodic table, then it goes down to the F's for F14. Then it comes back up to the D, the 5D10. All right, and this is 54, plus 2 is 56, plus 14 is 70, plus 10 is 80. We need 3 more, and so that is then the 6P3. So when you add those up, you get 83, which is neutral bismuth. There's no charge here. And so there is your electron configuration for bismuth. And if you wanted, if it was asked for the 4 quantum numbers for the 6p3, then you would have the first number is 6. P, S was 0, P was 1, so you'd have 6, 1. Then you would have to know that the P subshell has 3 orbitals. Always the one in the middle is 0, -1, 1. And we're putting in 3 electrons. And you have to know Hund's rule on how to put in the 3 electrons, which ends up in orbital number 1 with a spin of up, which is 1/2. And so the 4 quantum numbers would be a 6, 1, 1, and 1/2 for bismuth. All right. If you are asked about atomic radii, so if I had O versus F, largest atomic radii. All right, so F is the smallest. So if you're doing atomic, atom, neutral, radii, F is the smallest. So then anything compared to F is going to be larger. If we are going to compare an F minus versus an Na plus, and we want the largest ionic radii, all right, Now, the first ones were neutrals, and it's atoms, so it's an atomic radii. The second ones are charges, they are ions, and so it's an ionic radius. Whenever you're doing an ionic radius, you know that the more negative, the larger your radius. That means you have an extra electron, and it's way out away from your nucleus. All right, let's go to Lewis structures. The test is 90+% multiple choice, if not 100%. If there's going to be things that you have to do yourself, most likely they're going to be drawing Lewis structures. I like to know that people can draw a Lewis structure. One of my favorites is NCl3. And so you would have to do the Lewis structure for NCl3. We'll do it by counting the valence electrons, 5 for nitrogen and 7 for chlorine. All right, and so we have a total of 26 valence electrons. All right, and so the first atom is the central atom, bonded to 3 chlorines. That is 6 electrons. So now we have 20 electrons left, and that is the perfect number to give all of your atoms an octet. And so there is the Lewis structure of NCl3. All right, but now it's going to ask for the geometric arrangement. You have 4 directions, which means it's tetrahedral. It's going to ask for the hybrid orbital. There's 4, you need 4, and S and 3 P's, so sp3 for the 4 orbitals. Then you're going to have to give the molecular geometry. So let's show this in 3 dimensions. So you have to know what an octahedral or a tetrahedral looks like. All right, so it looks like this. So you got your electron pair, you've got your Cl, you've got your Cl, you got your Cl, you got your electron pairs around your Cl, and this is a trigonal pyramidal. All right, then the bond angle, 109.5. And then is this polar or nonpolar? So here you have to know the bond dipoles. Chlorine is electronegativity of 3.2 versus nitrogen's electronegativity of 3. And so the chlorines are all delta minus. Nitrogen is delta plus. And so your molecular dipole is here. And so you have this is polar. That is a polar molecule. All right, so doing these things, that is an important thing to know about chemistry. So definitely going to be on the test, whether it's multiple choice or write it out. I haven't decided that yet. All right. Let's do formal charge. Let's see if I have a compound that looks like this. All right, so you have to calculate the formal charge of each of these atoms. Hydrogen, always 1 bond, so all of these hydrogens are neutral. All hydrogens, 1 bond, yes. Nitrogen should have the 5 electrons around it, which is normally, as we saw in the last picture, 3 bonds in electron pair. That is not what we have here. We only have 4 electrons on this nitrogen. We were supposed to have 5. This nitrogen has a positive charge. Carbon should have 4. It has 4. 4 bonds to carbon, yes. 4 electrons, 4 bonds to carbon. It is a neutral carbon. Oxygen is in column 6. You have 1 electron from each of these bonds plus 2 and 2. So a total of 6. That's a neutral Oxygen, again, oxygen should have 6. This one has 6 already with the electron pairs, plus the 1 from the bond. And so this has a negative charge. All right, so you need to be able to do formal charges. Bond length, bond order, bond energy. All right, if we want to do the electron configuration for nitrogen gas. All right, so this one gets pretty difficult. It's when you have this thing. All right, and so you have for nitrogen is 1s2, 2s2, 2p3. 1s2, 2s2, 2p3. So that's the electron configuration for your nitrogen. And so you're going to have the electrons go here, then here, then here, then here, and then you have your 6 electrons, 1, 2, 3, 4, 5, and 6. And so you have a sigma 1s 2, you got a sigma star 1s 2, you got a sigma 2s 2, you got a sigma star 2s 2, you got a pi 2py 2, you got a pi 2pz 2, you got a sigma 2px 2. All right, and so that is your electron configuration for nitrogen. And so your bond order is a bond minus a bond, a bond minus a bond. So an anti-bond is a minus bond. And then a bond, a bond, a bond, 2 electrons per bond. So your bond order is 3, which is as high as you can get for a bond order. All right, and the Lewis structure would simply be 3 bonds between your 2 nitrogens. All right, if we looked at N2 plus, if we looked at N2 plus, that means we have to take out 1 electron. So we would remove the last electron put in. And if we did that, we would take out a bonding electron. And so now the bond order would be 2.5. We took out 1 electron out of the bonding electrons. All right, and so your N2, this is going to be a stronger, so bond order is 3, so this is stronger. And this would be a longer bond. So the lower the bond order, the longer the bond. The higher the bond order, the stronger it is. That's the more bonds between the 2 atoms. All right, so yeah, so stronger bond, that means greater bond energy. All right. Orbital pictures. Okay, so if we were to draw this N2, all right, so we have a nitrogen triple bonded to a nitrogen. So this nitrogen has 2 directions. 2 directions. All right, a triple bond is just one direction. and then electron pairs the other direction. So this is an sp hybridized nitrogen. Both of them are the same, sp and sp. So to draw an sp, you have your py and you have your pz. Your py and you have your pz. All right, and so your electron pair, you have your electron pair on each side of your nitrogen. Those are the electron pairs here and here. Those are in the sp orbital. Your sigma bond is an sp overlapping with an sp, the two electrons here for the bond. Now your py is going to overlap with your py. Your py is going to overlap with your py, where you have one electron above, one electron below, for the two electrons for that bond. Then your other pi bond, half of that pi bond is back away from you with one electron, and the other one is out in front of you with one electron. All right, and so when we have our N2 and we do valence electrons, we have 10 valence electrons when we draw our Lewis structure, and we see that we have 6 that are sigma electrons in the s orbitals. The lone pairs are in sp orbital, starts with an s, and you have the one sigma bond, and then you have your 4 pi electrons in the 2 pi bonds. So whenever you make a triple bond, the first bond is sigma and the next 2 are pi's. So that is drawing a bonding picture. All right, phase changes and phase diagrams. Okay. All right, if we have a phase diagram, we can have our graph. And you would need to know what's in A, what's in B, what's in C, what point is this D, what point is this E. So here is your pressure and here is your temperature. All right, and so you have to know that A is your solid, B is your liquid, and C is your gas. And then D is called the triple point. That has equilibrium between solid, liquid, and gas. And then E is your critical point. If they label a 1 atmosphere, let's say 1 ATM is, say, here, and they could have a point here, as call this one F. All right, and so if they have 1 atmosphere, F is the normal melting point. And then they would, well, it's a very ugly picture. Okay, so anyway, it's, say, there, your critical point is going to be way up higher. And so then if you label this one at the 1 atmosphere point G, that would be your normal. And what's meant by normal? 1 atmosphere, boiling point. So if they label the 1 atmosphere, then wherever it crosses a line, that is your normal. If it's solid to liquid, melting point. If it's liquid to gas, boiling point. Normal just means at 1 atmosphere. So if you have a phase diagram, it would look like that. If you have a cooling curve, all right, so here's my temperature, and here is time as you're cooling it. So you're going to throw some gas, you're going to condense it into a liquid, then you're going to cool it, and then you're going to freeze it into a solid, and then you have it in the freezer. And so you'll have a point, say here, a point here, a point here, a point here, a point here, and down here. So it'd be A and B and C and D and E and F, right? Oh, and let's put a point here, G. All right. So A is a gas. So A here is the gas. B is interesting. It is the gas at, that is a gas at your boiling point. Or you can call it condensation point. That's the same. It's in equilibrium. All right. But this is a gas at the boiling point. Now C is all liquid at the boiling point. If you are between B and C, G and C, call this say H. This is equilibrium. So you have your liquid and gas at equilibrium. So any point between B and C, this is your liquid and gas at the boiling point. All right, but if you're all the way to the left, then it's all gas at the boiling point. All the way to the right, it's all liquid at the boiling point. G is your liquid. D is your liquid at the melting point. And then E is a solid at the melting point. And then F is just solid below the melting point. All right, and so if you're anywhere between D and E, I don't know, G, H, I, okay, so this is going to have, if you have this spot right here, you have solid and liquid at the melting point. So that is an equilibrium between your solid and liquid at the melting point. All right, so if you're going to take a gas at, let's say, 120 degrees Celsius, and we're going to cool it water vapor. So the gas I want to use is water vapor at 120, and we want to cool it to room temperature, 25 degrees Celsius. All right, if we look on our diagram up here, we see that we're going to start here, and we're going to have to cool it down. Then we're going to have to condense it. And then we're going to have to go down to the liquid at 25 degrees Celsius. And so you would have to do 3 Qs. You would have to, the first Q value that you would have to have is to go from A to B. That would begin Q1. Then you would have to do Q2, which goes from B to C. And then you would have to do Q3, which goes from C down to G, the 25 degrees Celsius, where it is a liquid. So to find the energy absorbed by the water in order to cool it down to 25, you would have Q1 plus Q2 plus Q3. And that would be your Q total, the amount of heat removed from your water vapor to cool it from 120 gas to 25 degree liquid. It would require 3 calculations and adding those 3 numbers up. All right, phase change, phase diagram, crystal lattice, intermolecular forces. All right, so you'll have most likely a question, volume of the cube, that is A to the third, molar mass, L, density, and Avogadro's number. Remember, L is going to be 1, 2, or 4. It's either going to be simple, body, or face. Also remember that your A needs to be in centimeters. And so that's going to be some number times 10 to the minus 8 centimeters. So it's always some number times 10 to the minus 8 centimeters. And that is because your density is going to be in grams per centimeter cubed. All right, so units there are important. You have the equation, you plug it in, and you have to get a 1, a 2, or a 4 for the simple, the body, or the face. So review that. There will be a question using that equation. Intermolecular forces. The question would be CH3, CH2OH. Would be which one has the higher boiling point. And as soon as you see hydrogen bonding, that's your answer. That is going to be the highest boiling point because it has hydrogen bonding. So hydrogen bonding is a very strong intermolecular force, which would take a lot of energy to break that hydrogen bonding up in order to boil it. So that means it has a very high boiling point. All right, so then a good question would be if we have a 20% sodium chloride solution that has a density of 1.2 grams per milliliter. And this would be my one question, answer everything. And then delta H vaporization for water, 40.7 kilojoules per mole. And we are at 25 degrees Celsius. All right, and so here is what you would get for this one. This is many, many, many questions. So calculate little m, molality. Calculate mole fraction of the NaCl. Calculate the capital M, molarity of the NaCl. Calculate the freezing point. Calculate the boiling point. Calculate the vapor pressure of water at 25 degrees Celsius. All right, calculate the vapor pressure lowering. Calculate the vapor pressure of the solution. And finally, calculate the osmotic pressure. All right. So, of course, we're not going to have time to do all those things, but when you have a 20% solution, you assume 100-gram sample. That means you got 20 grams of NaCl, 80 grams of water, because we assumed 100 grams of solution. And with a density of 1.2 grams of solution per milliliter of solution, all you then need to know is that molality is moles. Convert your grams of NaCl into moles per kilogram of water. Convert that into kilograms. Mole fraction, find the moles of NaCl, find the moles of water. Moles of NaCl divided by moles of NaCl in water. Molarity is moles per liter of solution. Again, convert that to moles. You convert your grams of solution using your density to liters of solution. Freezing point, delta T sub F is equal to I Kf C sub M. Remember that we're talking about NaCl, which has an I value of 2. Kf will be given. C sub m is your molality. It's right there. Same as the boiling point. Delta T sub B, I, Kb, C sub m. Kb will be given. To get the vapor pressure of water, 25, you got to use the Clausius-Clapeyron equation. You find your pressure, so then you have your mole fraction, I mole fraction times the pressure of water that you found here. That's how much is going to go down. Subtract that. That's your vapor pressure of solution. And then finally, pi is equal to I MRT. All right, so you already have your I is 2, M is right there, R, you got to use the right one. We need a pressure, osmotic pressure, that's the 0.08206, and of course your temperature in Kelvin. All right, test is Friday at 8 o'clock in here.